Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on October 13, 2025, about 2 days ago. The striking result is a clear scale threshold for memory allocation in reasoning models. Below an effective size of 8-bit 4B, this paper shows accuracy improves more by spending memory on model weights, while above that size, allocating memory to longer generation wins. The paper is titled, "Not All Bits Are Equal: Scale-Dependent Memory Optimization Strategies for Reasoning Models." And as we'll see later, the implications for deployment choices are quite significant. Beyond the threshold, the study maps when higher weight precision beats 4-bit, when parallel sampling becomes efficient, and how KV cache eviction versus quantization shifts with model scale. Alright, the previous segment set up the scale threshold. Figure 1 charts accuracy against total memory, which combines weights and key value cache, for the QN3 family on AIME25. The curves show that models below the effective 8-bit 4 billion size benefit more from spending memory on higher weight precision and capacity than on longer generations. The inset highlights that 8 billion at 8-bit overtakes 14 billion at 4-bit, reinforcing the precision advantage for math-heavy reasoning. So, the previous figure contrasted accuracy against total memory. Table 1 lists the raw memory footprints, which anchor that trade-off across the QN3 scales. The left block reports model weights at 4, 8, and 16-bit. With the 8-bit 4 billion case near 4.2 gigabytes, matching the effective threshold. The right block shows key value cache growth, with token budget and sampling, which reaches about 117 gigabytes for 30,000 tokens, with 16 samples on the 32 billion model. Okay, Table 1 set the memory baselines. Figure 2 shows how Pareto optimal choices split between token budget and effective model size as total memory grows. The left panel indicates that below about 10 gigabytes, higher effective model size advances the frontier more than longer generation. The right panel confirms the flip side. Once memory rises, the best points cluster at large token budgets, often above 20,000 tokens, because longer chains deliver larger accuracy gains for bigger models. So the previous figure pushed the frontier toward longer token budgets for larger models. Figure 4 shows GPQA-Diamond memory versus accuracy, where 4-bit weights are broadly memory optimal because knowledge tasks favor parameter count over arithmetic precision. The curves trace increasing token budgets, and the larger models climb to higher accuracy with 4-bit precision. This pattern contrasts with AIME25, where 8 and 16-bit held the advantage for math-heavy reasoning. Well, Figure 5 examines how parallel sampling shifts the memory accuracy frontier on AIME25. The curves show that increasing the group size helps only once the model is effectively larger than the 8-bit 4 billion threshold, because added samples turn extra key value cache into accuracy. For smaller effective sizes, configurations remain below the best serial trade-off. As memory budgets rise, the memory optimal group size grows, clustering around 4 to 8 and then moving higher. The takeaway is that parallel scaling is a big win, only for large models with ample memory headroom. Alright, the previous figure showed when parallel sampling pays off. Figure 8 compares memory against accuracy for different key value cache strategies, and the dashed frontiers move up and left relative to a full cache. Both eviction and quantization improve the trade-off, which means higher accuracy at the same memory, or less memory for the same accuracy. Gains are strongest below about 10 gigabytes, where the cache dominates footprints. Alright, 2 takeaways stand out. There is a clear scale threshold around 8-bit 4 billion parameters, below which accuracy improves more from higher weight precision and capacity, while above it, longer chains and parallel sampling pay off. Second, key value cache compression is essential. The implication is simple. Deployment choices must be scale aware. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.